We're going to start dynamics now. Kinematics simply describes the motion. Dynamics looks for the root cause, the forces behind it. As always, a yellow star is highly critical material. A blue slide means it's an extension and not needed, nor will it be tested. The off yellow star with the number 12 is when I'm directly straying into grade 12 material for you to give you a heads up. You should be able to state Newton's 3 laws, calculate net forces on a free body diagram, use Newton's law F equals ma in a variety of situations. And these last 2 bullets are highly critical. Explain the order of causality. Does acceleration create force, or does force create acceleration? And express acceleration as either newtons per kilogram or meters per second squared. These last 2 bullets are necessary for deep understanding. You can become a mathematical whiz at Newton's law, but it's very easy to totally misunderstand the point. And it's amazing how many trained scientists still, they can calculate the orbit of a spacecraft, but they will make very simple misunderstandings of Newton's law. So if you don't get these last 2 bullets, you really, I don't think, can become an expert at this. You're mechanical, but you're not deeply understanding. The first of Newton's law is called inertia. You can go to my printed version, my online slideshow, and watch the video clips that I've added. We will do the videos live, but I'm not going to play a YouTube video inside of a YouTube video. These clips are out there, so why repeat things? The first law involves inertia. Objects in motion remain in motion. Objects at rest remain at rest unless acted upon by an external unbalanced force. What a mouthful, when all we want to say is your velocity is constant unless there is some total force on you that is not 0. And if the sum of all forces is not 0, then neither is acceleration 0. This means if you have constant velocity, not speed, constant velocity, then there is no total force on you. It adds up to 0, and if there is a total force on you that isn't 0, you're accelerating. And we'll see why it's velocity, not speed. Aristotle thought rest was some special state. So to say objects in motion remain in motion and objects at rest remain at rest is restating this misunderstanding going back thousands of years. Velocity equals 0 is not a special speed. You are at rest compared to the floor right now. But you are really moving very, very fast from the view of someone on the moon. You're moving even faster when viewed from the sun. And your stationary buttocks right now are speeding around the galaxy at 200 kilometers a second. Not hours, 200 kilometers a second. If you're next to a passenger in a plane, their speed is 0 compared to you. But from the ground it is not. 0 speed has no special meaning whatsoever, and speeds can be anything you want. It just depends on where you're measuring them from. Does the Earth have constant speed or constant velocity around the Sun? Don't worry about that the Earth's orbit is slightly elliptical. If you're a kid who's more interested in astronomy and you know there are small little weebles and wobbles, let's just base it on my drawing, that the Earth is in a perfectly circular orbit going around the Sun. Here are the 4 velocity vectors. The speed vectors are the same. If the Earth is in a circular motion, then the speed is constant. The velocity is not. This is because the direction is changing. And if you change direction in a car, you feel it. It takes effort to make a turn. So the Earth is not at constant velocity. It's at constant speed. You can detect a change in velocity because you should feel the acceleration. On a merry-go-round, the delta velocity is quite noticeable to you. Obviously, on the Earth, you don't feel the delta velocity as you spin around the Earth because it's too slow given the size of the Earth. However, storms, ocean currents, and long-range artillery shells really feel that bending force. The second law is a statement of the relationship between a force on the object and its acceleration. Now I'm dropping the summation notation, that's sigma, for our first glance because it just gets in your way. When we write force, we mean the leftover force. If you're pulling in two separate directions like a tug-of-war, nothing happens. F equals ma tells you that you can calculate the force on an object by multiplying its observed mass times its acceleration. But really, it is the force that causes acceleration. So Newton's second law should be written: acceleration is caused by a force acting on a mass. And if you look at this, this makes very eminent sense. The bigger the force, the bigger the acceleration. But look where mass is. It's underneath the fraction. So if mass goes up, acceleration goes down. So if F is applied to an object and the object starts gaining mass, the bottom number, then the acceleration goes down. My teachers tried to teach me this in grade 11 and I hated it. I didn't want to write the formula this way. I wanted to write it that way. It's easier to work with. But the truth is this form. And I want you to start thinking of a formula. It doesn't matter in math class. You could write ma equals F. But from an understanding viewpoint, you can consider a formula as acceleration is caused by force over mass. And that gives you more of an understanding of the nature of a real life phenomenon. Let's do a real simple calculation with it. I give you a car of 1,200 kilograms and it accelerates at 4 meters a second every second. What force does the engine provide? That's all it takes to use this formula. And you'll get really good at it within a single afternoon. Notice I put the units in a different color for you to draw it to your attention. And I put this what's called a mid dot. The dot for multiplication, so you don't ask me what's a kgm. It's kilogram meter per second squared. Now we have to figure out what those units are, but that comes next. They get called a Newton. But it's really easy math, much easier than the kinematics equations by a long shot. The third of Newton's laws is the instant karma. For every action, there is an opposite and equal reaction. Forces come in pairs. Look at Wonder Woman here, right? She has a pair of arms. So forces always come in pairs like arms. The misstatement of Newton's third law, for every action there is an equal and opposite reaction, it's missing part of that sentence. On different objects. If there were equal and opposite forces on the same object, nothing could ever accelerate. Not move, accelerate. So you can't grab your own head and lift yourself off the ground because you have equal and opposite forces on the same object. This gives probably one of the creepiest interpretations in physics, next to black holes and the fact that you've never touched another object in your life. And you'll have to ask me about that last one. You cannot accelerate yourself. Not once in your life have you actually been the force behind your changing speed. You can only push other objects, and in return, they give you a kick in the pants too. Let's look at a kangaroo jumping on Earth. You think the kangaroo jumped. It's actually the Earth kicked the kangaroo. Here's our equal and opposite force pairs. The force of the kangaroo on the Earth itself actually accelerates Earth. Turn the kangaroo on its back, put a giant blue beach ball on its legs, and let it kick its legs. Its legs made the other object accelerate. So, believe it or not, when the kangaroo jumps, the Earth recoils a little bit from the force of the kangaroo on the Earth. The Earth is much larger than a beach ball, so its acceleration exists in theory, but we could never, ever, ever measure it. But again, if you do the thought experiment and flip the kangaroo on its back with a beach ball, you will realize the kick of its legs will accelerate the receiving object. The force of the kangaroo on the Earth is what makes the Earth move. The Earth provides Newton's third law, an equal and opposite reaction force. The Earth kicks the kangaroo. It's like, what are you doing kicking me? Right in the Indian Ocean. Ah! And the Earth kicks back, and it's the Earth kicking the kangaroo back that actually puts the kangaroo in the air. So when you have jumped any point in your life, the surface you jumped off of is what you were driven into the air by. And it's so hard to imagine that. But let's conduct two more thought experiments. When you are on a trampoline and you jump, what really threw you in the air? Your muscles or the trampoline surface? There, it's much easier to believe Newton's third law that you were driven into the air by the trampoline. But let's conduct another thought experiment. The kangaroo finds itself suddenly lost in space. And all the kicking in the world now will not help Mr. Kangaroo. He will just drift away in space. His legs are useless if he doesn't have something that will kick him back. Otherwise, he could still jump while he's out in the depths of space. So Newton's third law is a really tough one to fully appreciate what this really entails. Now let's take a look at some applications of these two laws put together. Canoes have a mass of about 25 kilograms. A paddler has a mass of 60 kilograms. He jumps out of a canoe using a force of 85 newtons. Calculate his acceleration and the acceleration of the canoe. Seems like a lot at first, but not really. We got a mass of a paddler and a force. So the paddler is going to exert a force. He's going to kick with his legs 85 newtons, and it's on his mass of 60 kilograms. So the paddler will accelerate forward at 1.4 meters per second every second from his jump. Now, there's going to be an equal and opposite force on the canoe. So we take the exact same force, but we apply it to the canoe body. And the 85 newtons occupying on the much lighter canoe will cause the canoe to accelerate in the reverse direction at 3.4 meters per second, more than double the acceleration of the jumper. And this causes an effect that is famous on people who do not understand how not to get off a boat.
Yeah, okay, I'm recording.
I want to see you jump off with her on.
That's what he's gonna do.
Okay, so this is 1 meter.
When we look at a clip like that, what we see is his attempt to jump off the boat, even though he didn't want to grab the rope. When he made an attempt to jump, he actually pretty much dropped straight in the water because the boat so swiftly accelerated away from him, you get an unexpected, hey, I'm over water. So jumping off a boat that is small the boat's recoil acceleration is going to swiftly take your legs out from under you. And if your legs start moving out from under you, you just tumble forward. You rotate around your belly button. There are two ways of writing Newton's law that I keep going on about. F equals ma and A equals F over m. The upper formula is the easiest way to write, but it creates the impression that the force was created by the observed acceleration. The lower version is the correct way to conceive of this law, that the force acting on a mass caused the acceleration. This is the proper way to view Newton's law from a conceptual viewpoint. I'll get rid of the sum notation so we can see it in its simplest form. The confusion occurs when people go, where did the force come from? In most of the problems we deal with, it's a jet, it's a rocket, it's a human being lifting something, and we tend to give you the value of the force, or we give you the behavior and you calculate the value of the force. But none of that deals with the origin of the force. Where did the force come from? The most obvious one, the one that Newton set out to formalize in 1665, was the force of gravity between two objects. We look at the force of friction between an object and another surface. We'll study the elastic force when we store energy in a spring. You'll look at the magnetic field force around a wire. You've seen junkyard magnets where they turn on a big electromagnet and they can lift things up. That's the formula for that. And finally, you'll look at Coulomb's law, which is the force between two charges, like a proton and an electron. It looks remarkably like Newton's law because our universe is three-dimensional, and this law and the gravity law are direct outcomes of that three-dimensional structure of our universe. These 5 equations will form some of the backbone of your work in physics and chemistry, and you will study them next year, and we'll look at them a bit here. But I wanted you to see that the force itself has a source, and we don't discuss that enough to make it clear that there are other equations that would go in to giving us the force value in the real situation. We tend to stick with gravity in grade 11. By grade 12, you'll be going to charges and elastic energy.